So before goes to some details about the temperature, I have to introduce another parameter. Actually, it corresponds to the temperature, which is called the nominal operating cell temperature. So what does it mean? Actually, it's some parameter which can characterize the properties of the model, and it's some kind of temperature of the solar cell which would be achieved for the cell when the module, I mean the solar cell, which is already encapsulated solar cell in the model, when the module is placed on some standard operating condition. It's changing, it's a different thing. It's not a standard reference condition, it's some standard operating condition, which is actually a little bit more near to the real condition. So I can give you just some examples that, so we can sometimes you can find this this parameter, nominal operating cell temperature. You see, it's approximately 50 degrees. So actually, it means that again the temperature of the solar cells is here. It's 48 degrees, 0.4, but actually it's when the module is irradiated with this actually is placed in the standard condition, which means that the temperature of the air is 20 degrees. The intensity of solar light it's not 1 kilowatt, it's only 800 watts per square meters. And there is some specification of the speed of the wind speed, but you should be a little bit careful with this value, because actually it's quite hard to estimate, to determine this nominal operating cell temperature with precision better than plus minus 2 degrees. It's why I was a little bit skeptic about this value of 48.4 degrees. So actually it's almost impossible to measure it. It means it's the minimum value they can obtain, because the lower temperature of the solar cell, this condition, the high efficiency we can get. But it's quite too difficult to determine precisely this temperature. So first of all, you have to measure the temperature of the solar cell, which is already encapsulated in the module. Then there could be some deviation in the irradiation, because actually this measurement means already outdoor measurement of the module, because at least you have some condition about the wind. So it's quite hard to get this ideal condition. And actually there could be some influence of some secondary parameters, like if you have an installation without any distance, for example, to the roof or to the wall, you can change your cooling condition, so dissipation of the heat. So if you have some gap between the roof, so you can improve a little bit the cooling. So there are different parameters which can affect the real temperature of the solar cell, for what I mean. and actually the wind direction is not specified, so you can find some optimal condition to get the best value. But at least it gives some ideas. For example, when you have seen this 48 degrees, so it means that you can expect something about 50 degrees at this nominal operating condition. So, and from this value of the temperature, you can estimate the temperature of the solar cell for the more or less real condition. So, using this quite simple formula. So, what is the idea? The idea is to get the value of the temperature of the solar cell which is placed in the real condition, because as I told you, any parameters which is given, any electrical parameters like open circuit voltage, short circuit voltage, and main the power, it's given for standard condition, but it depends on temperature. And if you want to estimate, if you want to buy some solar station, for example, you want to buy, you have to decide how many models you have to buy. So you want to get some, let's say, 2 kilowatt, and you say, okay, normally I can buy 20 modules of 100 watts each. But when you mounted them, get any installation, so a lot of investment, and then you have found out that real power is not 2 kilowatt, it's less, it's, let's say, 1 kilowatt, 800 watts. Why? You call to a producer and they say, okay, but it was indicated that the power 100 watt is only for the standard condition, and your real condition is different. You have at least, you see, if you are this more or less comfortable condition for solar cells, so you have a 20 degrees, so you have some wind, so you have a intensity, so maybe for power, you see it's clear, for power production, less the light you have, less the power. But even for the efficiency, it gives some deviation. And for this, for real models, normally have a 50 degrees, while the standard condition is 25 degrees. You see the difference of 25 degrees. Now I will give you the values, but just to explain why do we need this equation, is to estimate what would be the real temperature of the solar cell when it's installed, for example, in Sahara. So see, temperature of the air temperature could be, I don't know, 50, 60 degrees. You have a lot of sun and a lot of heat, so you can get, I'm afraid to estimate this value, but it could be even 80 degrees, something like this. And now, what happened with solar cells when the temperature is changed? So, actually, to describe this difference, it was decided that the simplest way is to make some linear approximation of this temperature dependence using this, the coefficients by this way. So we have some, so it's an approximation, so it's some kind of simplification, the simplest way, but it already gives some ideas about the behavior of the solar cell, first of all, at least to compare them. And what is the most important, you can get some estimation. So if you have the typical values of this coefficient for the silicon solar cell, you can see that the VOC value, it's negative, so this coefficient is negative, so it means that the VOC decreases with the temperature increase. And this decrease is quite significant. Fortunately, short circuit current increases, but this increase is not so important. I mean, compared to the VOC, is not so significant, and normally few factor decreases also. And in summary, we have a decrease of the power. So I would say for any semiconductor solar cells, if there is no some problem inside with some parasitic barriers, etc., VOC decreases, short circuit current increases. For few factors, there could be some different things. In the most cases, it decreases also with temperature, but it depends. And the power generated by the solar cell always decreases. Power, I mean the power and efficiency. So it's, when I say power, when I say efficiency, it's, you see, it's the same thing, because efficiency is it's a relation of this power divided by the power of the incident light, the power of the incident light. Now it's some fixed standard condition, so it's no change. So, just few words why it so happened. For increase of the short circuit current, it's actually for any dependence, there could be many factors with many difference, but the main factor for the short circuit current, it's well-known dependence of the gap on temperature. So you have a decrease of the band gap with the temperature, and normally it means that you have here you see. So if you have a decrease of the band gap, so it means this border is shifted toward the higher wavelength. So it means that your solar cell could convert the wider spectrum of wavelength of would say of photons. So sometimes for multi-junction solar cells it's always a question, but for multi-junction solar cells everything is more complicated. But for single junction solar cell, it's a main mechanism. I'm sorry, it was not right. For VOC, it's a little bit more complicated. Maybe you know there is some effect of which is called the statistic shift of the Fermi level. It means that when you heat a semiconductor, Fermi level wants to go toward the mid gap. So it means that your Fermi level is shifts. Actually, it's better to describe like this. So you have so it's a N, it's a P type, and actually this is so-called built-in voltage or diffusion voltage, but this the change, the bending, actually it represents the VOC. Actually, it's not always the same, but the higher you have this bending, normally the higher you have a VOC. So you can increase the doping of each layer. So it means if you increase the doping, the ephemeral level, it goes near to the nearest band. So it means that you have some kind of increase of this band bending. But with the temperature, the concentration of the electrons and holes in equilibrium is the same. And you know, for example, the concentration for electrons could be expressed by this way. Some NC, it's the effective density of states in the conduction band. Then you have an exponential behavior, and minus the difference between the position of the ephemeral level and the nearest gap. So it's a conduction band, and it's AC and EF. So you have this minus difference. So it should be negative value. You see minus position of the ephemeral level. So we can call it like delta something, etc. Divided by kT. So this concentration is related to the doping density, which is not changed. So it's changed with temperature, but changing is quite small compared to this exponential behavior. Temperature is changed. This factor is not changed. So there is only one way the position of the ephemeral level should be changed. So it's like goes toward mid gap. But you see the ephemeral level should be the same for the p-n junction in equilibrium. So it means that for the higher temperature, you have these changes. So it's like this. So if I fix this in this value, it's like this. Yes. So I have to, yeah. And here also there is some shift. So it means for this band gap at higher temperature, we have a small built-in voltage. So it's the main. I mean, there are different factors also, but it's the main reason for decrease of the VOC with the temperature. And it's some kind of, the both are fundamental. So you cannot change anything here. It's a fundamental properties of the materials. So the only one thing, you have changed the materials. And so just to finish with this slide, I want to say again that if you know this temperature coefficient, which is normally is known it's for solar cells, and if you know the temperature, the real temperature of the solar cell, you can calculate or at least estimate the main electrical parameters of a solar cell. So you can estimate the maximum power, and we will see intrinsic circuit current. Sometimes it's you need them to make some estimation of the some electronics. So, but as I told you, just want you remember that for the same condition, the solar cell at high temperature have a lower efficiency compared to the solar cell at low temperature. Yeah? So this increase of the temperature leads to the decrease of the efficiency. Concerning these pictures, I mean, you have to understand that if here you have a factor of 2 or 3 more light, of course you will generate more light. So you can compare the power for the same solar irradiation. But if you have 1 kilowatt per square meter here and the same, but the difference in temperature is important, so you would have a higher generation for the solar cells which are placed in colder places. And as I told you, you cannot, so you can do something to improve the solar cells by these basic properties is rather related to the materials, and it's why you can get some ideas about the temperature coefficient for different materials. So you can see that in general case you have some kind of dependence. It's not indicated here, but it's like it depends on the gap of the material. So because here the gap is increased, and you see the temperature coefficient, this negative temperature coefficient, decreased. So for the higher gap. So for example, for silicon you have 1.12 eV. For gallium arsenide it's 1.42 eV. So you see higher. Oh, of course, there are different parameters which can affect also this temperature dependence, and it's why it could be some. There is some kind of range of this parameter. Another thing, it's amorphous hydrogenated silicon. It has low temperature dependence because VOC decreases slightly because this history is not for amorphous hydrogenated silicon. For amorphous hydrogenated silicon, we have so-called pinning of the Fermi level. It's in opposite. The position of the Fermi level is like a fixed by the defects because you see amorphous silicon is a material with a high defect concentration. And then if you heat amorphous hydrogenated silicon, you can see a difference, some increase of the concentration of electrons. It's another thing, but I mean it's one of the reasons why it's so slow. So now we can go to the next part of this topic. Just check time. Okay. So we understand that we have to provide some standard condition. And now the question, how to do it? So for temperature, more or less clear, but how can we produce this solar light? Let's say this, even a standard spectrum, but so of course the most part of the measurements is done using indoor measurements, using special devices which called the solar simulator. And in general we can select two types of solar simulator. It's a continuous light and flash solar simulator. Continuous solar simulator normally is used for unconcentrated radiation. 10 sun, it's a huge value. I mean, normally it's 1 sun, a little bit high just to get. For example, 10 sun, it's only to provide some fast light-induced degradation. It's not to get some concentration measurement. And the area is limited. So I wrote a small area up to 30 by 30 centimeters. From my scientific point of view, It's a huge area. I mean, normally we work with smaller cells. Most comfortable size is 1 by 1 or 2 by 2 centimeters. It's already a large solar cell. But for industrial point of view, it's a small size, so it's maximum 1 wafer. So it's not, you cannot use a continuous solar simulator to measure efficiency of the model. So in opposite, flash solar simulator is used for the concentrator. Concentrated solar cells, when you can get concentration up to 10,000 cells. Normally 1,000 is enough, but I mean, you can engineer this machine. And for industry, it's used to make characterization of large area of the, to measure the models. Concerning the solar simulator, first of all, we have to specify the main requirements. So, first requirements, it's clear that the intensity of the solar simulator should correspond to the intensity of the standard, should provide standard condition, at least 1 kilowatt per square meter. But in some specific cases, you may be required to lower or high intensity, so it depends on your requirement. But if you want to say that it's a solar simulator, this device should provide 1 kilowatt per square meter. Another most important requirement is the spectral match. So you see the spectral distribution of this radiation should correspond to the standard spectrum. So you have seen the standard spectrum. It's quite complicated spectrum. And how can we get it? Of course, we cannot make a perfect fit of this spectrum. We can just divide it by the different range. So normally you see it's a range of 100 nanometers. And we have to provide the required integral intensity within this range. So you see the ideas. So we divide the solar spectrum by the ranges, and our task that within small range the total integral intensity is the same as for the standard spectrum. So later I will show the picture. And there are two another important parameters which should be also provided. It's a non-uniformity of the light and stability. But I think it's clear that if you want to perform some measurement, some optical measurement, so the radiation should be uniform, because if you use some reference cell, for example, small reference cell to calibrate the intensity, and then you use a large test cell to be measured, and if you have some non-uniform distribution, for example, you have a spot of the high intensity where you have calibrated your solar simulator, and then outside the spot intensity is lower, so we get a lower value of the you would underestimate the efficiency of the power and other parameters. And of course the temporal stability is quite important also, because you see it depends on the range, but if you calibrated your simulator, you decide that now it's 1 kilowatt per square centimeter, per square meter, and then you change or make some measurements, and when if intensity changed, you see it's impossible to use. It's I think it's clear, so it's quite it's obvious, but I pay attention to these parameters because it's some kind of requirements, and if you have a look to the different solar simulator, you can find that there is some kind of classification of the solar simulator using the letters A, B, C, and for 3 main parameters which are required: the spectral match, spatial uniformity, and temporal stability. You can find the different class of simulator. For example, A, B, it means that you have a nice spectral match, but non-ideal uniformity and temporal stability. So the best simulator is the class AAA, and sometimes you can, it's not some, it's quite usual, you can find it, but then you have to pay attention to the area, of your illuminated area, because as I will show you, it's more or less easy to get the spectral match. Some electronical parameters, I would say, using electronics, you can get good temporal stability, but spatial uniformity, it's the most hard thing to be achieved, and it depends on the area. I mean, so it's more or less easy to get nice uniform light within a small area, but for the larger area it's more and more hard. And actually it's quite easy to understand, because if you have a look to the price, you can see that the highest price would be for this simulator with a nice spatial uniformity for the large area. So it's just scalable. What is a solar simulator? How does it work? What is the design? So here is some, I would say, usual classical design for continuous solar simulator. The heart of this simulator is a xenon lamp. It produces the light, the solar light. Then using ellipsoidal reflector, you can get almost parallel beam of the light, and it goes through a very important thing which is called the optical integrator, or sometimes it's called the homogenator. So it means that it makes your light more uniform, because I'd like to say, you can see, maybe you cannot see here. Actually, this is a picture of the lamp and the reflector, and so you can see here. So the lamp has an electrode, and so had to connect this electrode using some wire. So and the light goes here. So you can get some shading of this light, and to avoid this. The influence of this non-uniformity, we have to use some kind of this integrator. So actually it's a matrix of the different lenses which make some kind of mix of the light. Then optical filters is used to correct the spectrum. I think it's one of the most simple things, just to buy the filter. Oh, if you can, because for example, it's funny, but some producers, they can, so normally you can order any part of the, or at least many part of the solar simulator, like a lamp, filter, optical filter, from the order from the producer. But I have experience with one producer. When I asked for this optical filter, they asked me if I have a solar simulator of the company, and no. Or if you have no our solar simulator, we cannot buy this filter. But you can buy it from another producer, so it's not it's some specific case. I would say you can if you want to realize your solar simulator yourself, this part could be achieved. I mean, we don't need to make some special design to create this filter. You can buy it. It's one of the simplest things. So, and then light goes through last leads to collimate the light, and it's nice. Here is examples of the spectra obtaining using a different simulator with the xenon lamp. Because why do we need do people use xenon lamp? It's corresponds quite well to the solar light. So you see the baseline, it goes very nice, at least in this visible range. For near infrared range, you have a set of some peaks, but using the filter, you can deduce the intensity of these peaks. And then, as I told you, if you divide this spectrum by the different ranges, you can obtain the case where within one of this range you have the same intensity as for standard spectrum. So, sorry, the blue line here and red line here, it's a standard spectrum. I'm 1.5 G, it's indicated here, and the black line is a different solar simulator. And I would say the best source of the light is a xenon lamp. For xenon lamp, if you want to order some to create or order some lamp for the simulator, you have actually some option because solar simulators are produced not only for photovoltaics and for some biological or agricultural uses, and there is some option to get UV light, high intensity of UV light for this simulator. And actually for the solar for photovoltaic application, you don't need to use it. It would be better to use ozone-free, so-called ozone-free lamp, because so you see it's a UV, say UV enhanced. The spectrum of UV enhanced xenon lamp here. It has a high intensity in short wavelength range, and actually it produces ozone. And you know, ozone, it's not good for the health. I would say it's dangerous, and the simplest way to avoid this problem, because you have to care about the ventilation, etc. The best thing to avoid this problem is just to order so-called ozone-free. For example, it's some example of specification of the lamp for OSRAM lamp. So OFI means that it's ozone-free. It has some absorbing layer, and you can work without any special ventilation, etc. Just a room application. So, as I told you, the simplest way to get the spectrum match is to use the xenon lamp and the filters. And here you can see the influence of the different optical filters. So the black cube, it's a xenon. Red, it's a xenon lamp with a filter to get IM0 and green line to get IM1.5G. So you see, it just to illustrate that if you have a look for the spectrum like this, you can say, oh, there are a huge difference. How can we get? Why do you think that it's a nice spectrum match? But if you have a look to this picture, you can see that actually the filters which are used, it gives a lot of improvement. I mean, you cannot use the xenon lamp without filters if you want to get a nice spectrum match. But concerning the spectrum match, the last few words about we have a break. I would pay attention that this classification here, so you see the range is from 300 to 1200. The same when we speaking about spectrum match. It's given for this, again, this range 300, 1200, and actually it means that when you find some solar simulator of spectrum match A, it's only in this range. So it's nice for silicon, but if you are thinking about some wider range for multi-junction solar cell, for example 3-5 multi-junction cells based on germanium, you have to think about, so at least you have to care about the spectrum match, about the source, etc. Actually, a xenon lamp is not so bad for this application. I mean, even for up to approximately 2 micron, it gives not so bad spectrum match. But if you have a look for the different type of solar simulators, you can find. So if you compare for the other type of lamps, just quickly, halogen lamps, it's very nice to use because it's very convenient to use halogen lamp. You don't need to have some special source of light, but unfortunately spectrum is too in infrared part, and it's quite, so if you even increase the intensity of the wall intensity, you cannot obtain the required short wavelength intensity. Another type of arc like mercury or metal halide, so the main problem it's the peaks. Actually, xenon lamp already have some peaks also, but due to this baseline, it's acceptable to work with. But for other type of lamps, it's not a good idea. And it's how does it look, the solar simulator? And the way to get the better temporal stability is to use feedback. So actually it's not seen, but you have some optical fiber which follows the light into the detector, which is the special conditions to cool detector, and it gives an opportunity to get some feedback to correct the intensity in situ. And here is some example from a producer that they can improve the temporal stability. If you want to decrease intensity, it's not so obvious also, because I mean normally you cannot change the intensity of the power, because it would change the spectrum. So you can, but it just to adjust the intensity in quite small range, especially for xenon lamp, it's very limited. But if you want to decrease intensity in high range, so you have to use some natural filters, so which does not affect the spectrum. The simplest solution is to use some metal grid, so just no influence to the spectrum. So, and finally, this is some example again of the solar simulator and specification. So it's a data sheet for solar simulator. You can see that for each parameters it has a class. You see that for uniformity it just a class B. Now you can find a class A, it's not a problem, but just some indication that it was obtained the spectral match, temporal stability, no problem. But for uniformity it's not so easy. Actually this means that you can it's available and required, so it's if you pay you can get everything, but it's more expensive. So I think for today it's all. I mean for today, for this lecture. So, and today we have another lesson. Yes.